Okay, let me share my screen first. Is my screen visible?
Yes, mom.
Okay then. So let us start with today's class. So today is our second last class for the course, Technologies for Clean and Renewable Energy Production. So the content for today's class, as we know that we have studied about solar energy and wind energy in the last class. So we initially, in the start of this course, we studied about non-renewable energy sources, and then we transitioned towards the renewable energy sources. So in the sorry, last class was the first class or renewable energy sources, in which we studied about solar energy and wind energy, the most used renewable energy. So today we will be shifting towards the some other renewable energy sources. So first one is the hydro energy. Then second one is geothermal energy, and the third one tidal and wave energy. So we will be giving a brief introduction of what these energies are, then their mechanism of producing energy, and some of the classification and some of the machinery used in them. So we will be talking about all of these. So firstly, we'll be talking. Let us come to the hydro energy. So what is hydro energy? As we have talked in the last class, solar energy and energy. As we know that solar energy is the energy produced from the sun, the energy given by the sun, and wind energy is the energy harnessed from the kinetic energy present in the wind. So similar to the wind energy, hydro energy is basically the energy that can be harnessed from the kinetic energy that is stored in the flowing water. So basically, let us talk about firstly hydrologic energy. This is the basis of hydropower. So what happens is we all know about the water cycle. What happens is the water gets evaporated from various water sources such as oceans and rivers. It gets evaporated and then forms clouds here and gets precipitated in the form of rain. And this rainwater, it flows to dams and rivers. And in the rivers, due to the motion of these rivers, due to the motion of this flow of directional flow of water, contains kinetic energy, and this kinetic energy is harnessed by this kinetic energy is harnessed by installing some kind of turbines into these rivers and lakes and canals, etc. And this flowing water turns in the turbines. It absorbs, it takes the kinetic energy, and then this turbine is in turn is connected to a generator which converts this energy, this mechanical energy, uh, to electrical energy. So this is basically water cycle is the basis of our hydropower. So coming on to the mechanism of hydro energy production, what happens is we get the flowing energy, we get the kinetic energy from the flowing water from dams, then water flow in like rivers and canals, then the tidal barrage and what wave power in the tides also. This is energy from tides and waves in ocean. All of them we know that water here is in motion. So in motion it is, so it consists of some amount of some kind of kinetic energy. So this kinetic energy, this water, flowing water, is when it falls on the turbines, the wings of the turbine, they rotate, and rotate a shaft which is connected to the generator, which in turn here kinetic energy of flowing water is converted to mechanical energy in turbine, and then this mechanical energy in generator is converted into electrical energy. And after absorbing this kinetic energy here in the turbine, this tail race, this energy, this water, without the water, after absorption of the kinetic energy in the water flow, water is released from the other side of the turbine, which is basically called the tail race. Here, the kinetic energy is reduced. So, after in generator, it is converted to AC power. Coming on to the mechanism, the mathematical calculation that is involved in the hydro energy production. So the energy production from water, it basically depends on some factors, which is the amount of discharge of water, basically in meter cube per second of Qmax. Then the head in water, basically the difference of the height of the water flow. If suppose it is flowing from a height, then the difference of the height from water flow to the turbine is that is the head. Then efficiency, overall efficiency, which involves the efficiency of different instrument, different machinery involved. That is, as we have seen here, that turbine is involved, generator is involved, gearbox, and all other things are involved. All the mechanical machinery which is involved, the efficiency, overall efficiency is dependent on all the on the individual efficiency of all these machinery parts. And then the density of water, because obviously we are talking about the flow of water, so the density of water. So basically, power in what it is given by efficiency into density of water into this is gravitational pull, and this is discharge into head. So if this is in kg per meter cube, so if we put the value of G, which is 9.81 meter per second square, if we put it here, the value of G, then we get 9.81 into efficiency into uh, discharge rate of water into head. And it is, if we put this row also 1000 and divide by 1000, obviously it is in watt. And if we multiply with 1000 and then divide by 1000, then we get this in kilowatt. So power in kilowatt is basically 9.81 into efficiency into Q into H. And if we want to calculate the annual energy generated from the flow, so then it is calculated by time into power. So time is basically it is given in hours. So it is time into 9.81 into eta into Q into H. Now coming on to some of the components of hydropower plant and their role. So hydropower plant consists of basically three components: the civil components, then the hydropower equipments, hydromechanical equipments, and the electrical equipments. So civil work is basically all this concrete structure which is made to diversify the flow of water. If suppose this is the dam, so we need to water needs to be flown in a directed stream. So to make this directed stream path, we make some kind of civil structure, all this civil structure and this powerhouse and all this comes under civil structure for the control of water. Then the second part is the hydromechanical equipments. Basically, the hydromechanical equipments it consists of basically the turbine part, which is involved in the conversion of the kinetic energy present in the water flow to mechanical stream. So this is here, this part is the turbine part. So it is basically involved in the hydromechanical equipments. And the electrical equipments and power evacuation is basically the generator part, the part involved in the conversion of mechanical energy to electrical energy. So here, this is the generator part and this powerhouse. All this is involved in the conversion of mechanical energy to electrical energy. So basically, these three parts are involved in the conversion of hydro extraction of energy from the flowing water. So classification of hydropower is done in various forms. So on the basis of generation, it is on the amount of power that can be extracted. It is of various types: the pico, micro, mini, small, medium, large. Depending on pico, it produces a power less than 5 kilowatt. Then micro produces from 5 to 100 kilowatt. Then mini produces from 100 kilowatt to 1000 kilowatt, and then small produces 2 megawatt to 25 megawatt, and medium plant produces a power of 25 megawatt to 100 megawatt, and large uh, plant produces a power of greater than 100 megawatt. And it on the basis of head mean on the difference of the uh, height from the water flow to turbine. It is dependent. It is also it is divided as ultra low, which has a high head height less than 3 meter. Then low has a head height of 3 to 30 meter. Then medium has 30 to 75 meter, and high has 75 meter or more than that. When classification of hydropower on some other aspects are also done, firstly on the basis of purpose, either it is for single use or multi-purpose project. That means a hydropower plant, if it is only for either if it is for only power generation or only for irrigation purpose, and multi-purpose, it has various purposes. For example, this Tihri Dam has three different purposes. For it is used for all irrigation purpose also, power generation also, then drinking water also. Then classification based on hydraulic features: conventional hydropower plants, which utilizes the available hydraulic energy of the flowing water. All the existing plants are of this category only in India. And the pumped storage recycle mean all these are this conventional hydropower plants are basically made on the rivers or canals only. Mean not artificially. These pumped storage plants are made mean some kind of artificial that storage or water storage tanks are made on different heights, and using pumps, water flow is done for extracting energy from this flow. And then another kind is the tidal power plants, which are present only at the shore sides, or I mean near the sea, beaches, etc., on the coastal areas only. Classification on the basis of operation, that is the isolated plant and grid connected plant. Isolated plants are basically if they are, if a single plant is used for a single purpose and single area only. Not connected widely to different areas, only for a single area. For example, this Khopoli hydroelectric project for is used for Bombay only. And grid connected are connected nationwide or state wise. Okay. Coming on to some different kind of hydropower schemes, there are basically four kind of hydropower schemes. The first one is run of river. So let us talk what is this run of river. As we can see that here, this is the main river flowing. So we have diverted this river into a small stream. We have diverted it by forming some kind of construction, civil structures here. And so we have diversified a small stream from this main river here, and a desilting tank basically is used for the settling of some silts and clay, etc. If some kind of heavy particles are present, sand, etc., which it can be done here in the desilting tank. And then this stream comes to here to the forebay. The purpose of this forebay is to maintain the constant flow of water. A constant amount of flow. Varying velocity and varying amount of water it can come. For example, if we see this natural flow, we cannot say that constant velocity and constant amount of water is flowing here. But here, for continuous production of electricity or energy from this flow of water, continuous and constant velocity and constant amount of water should flow. So this four bay tank ensures that constant flow. And this uh, pipe here is for the flow of continuous flow of water to the power station, where this flow of kinetic energy present in the flowing water is converted to mechanical energy, that in turn is converted to electrical energy. So this stream is called the penstock. And here it comes where it is converted, where turbine and generators are present in the powerhouse. So this kinetic energy is converted to firstly mechanical energy using turbine, and then this turbine, and then generator in turn connected to the turbine converts this mechanical energy to electrical energy. So this is basically the run of river. Another kind is the canal fall based type. So what happens is, this is the main river stream, or basically it is canal, basically based on the canal types. It is not done on the rivers, but on the canal. So this is a canal. This is the main canal. So a diversion is made from the main canal, and here this diverted canal flow of this diverted canal is used for the conversion of kinetic energy present in this water to electrical energy using in this powerhouse. And after the conversion, this tail race is the water, water devoid of the kinetic energy. Here also we can see, after conversion of after all the conversions, tail race is given out to the main river. Then the third one is storage dam base. So in the dam base, what is done? The civil structure is made for storing for stopping the continuous flow of the water. So huge amount of water gets stored behind the dam, and then from here a small penstock is made, from where constant flow rushing water comes into the powerhouse, where all the conversions takes place, and from here this tail race is given out. And the third type is the pump storage type. In this is a kind of artificial made power plant, in which there are two different tanks are made at different heights, and using pump, water is made to flow. And the kinetic energy present in this flowing water is converted to electrical energy. So electricity is not amenable to direct storage, primary aim being to generate power to tune the demand to tune of demand in the grid at all times. So basically, various arrangements are possible. Well, for essential requirements of this pump storage power plant is two reservoirs with a high difference in water level between the two. So it is possible that both the reservoirs may be on the same river, or two reservoirs on two different rivers are present, or higher reservoir and artificially constructed pool, and lower reservoir on a natural river, or a lower reservoir is a natural lake, while the higher reservoir is artificial. So any of these four arrangements can be possible for pump storage power plant. Coming on to the advantages and disadvantages of hydropower and hydro energy. So the main advantages are, as we all know, that it is emission free, pollution free, no emission of COX, NOx or SOx, and it is renewable source, and it has the highest conversion efficiency, even more than the solar power or wind power, or any kind of that petroleum and coal and gaseous fuel energy. It is the conversion efficiency is highest in hydropower. So dispatchable with storage capacity, it is easily dispatchable, usable for base load peaking and pump storage application, scalable. Well, I mean, large scale power plants can also be installed easily. Low operating and maintenance cost, as the maintenance cost is low, so there is no such problem in installing different plants, and it is long lifetime. Remember, it is available for lifetime, as it is obviously renewable. It also has some disadvantages. So frequent involvement of impoundment of large amount of water with loss of habitat. Obviously, if we want to install some power plant, then the as we know that if suppose a dam needs to be made, so there is a large loss of habitat. Mean people mean Villages need to be relocated, and trees need to be cut. Animals lose their houses. So there is this problem, an environmental problem related to this. And variable output dependent means depending on the rainfall and snowfall, output may vary. An impact on river flows and aquatic ecology. Obviously, that aquatic ecology gets affected. That fish sometimes needs to migrate, and then oxygen depletion is a problem. Social impacts of displacing indigenous people, obviously, during the formation of dams and these hydropower plants, there is displacing of different habitats. Villages gets destroyed, villages, towns get destroyed for the formation of these hydropower plants. All the villages and habitat that is coming in the path of the formation of these plants, they need to relocate. Health impacts in developing countries, high initial capital cost is obviously high. Initially, during the building of this power plant, there is high capital cost required. Then long lead time in construction of large projects, and obviously initially large time is required for the construction of these projects. Coming on to some of the global scenarios, so these are some of the world's largest dams and hydropower generation. It involves this three jords in China with the largest capacity of 18,200 megawatt. Then in Brazil, Venezuela, US, Russia, Canada, Romania, there are different hydropower generation plants with very high generation that power generation, but the largest is the one in China. These are some of the large hydropower projects in India. Uh, the one in Bhakra on Satluj River, then in Dehar, then Kalindi Stage 1, Saravati, Koina, Nagarjun Sagar, Iduki Stage 1, Sri Sailam, Salal, Randi Sagar, then Chamera, Tiri Dam. All these are available in India with the largest capacity of Tiri Dam. As we can see, it has the largest capacity of 1400 megawatt on Bhagirathi River in Uttarakhand. Coming on to some of the hydromechanical equipments which are widely used in the conversion of kinetic energy to mechanical energy. So, water turbine, it is a rotary machine that takes energy from moving water. Flowing water is directed onto the blades. The water is directed onto the blades of the turbine runner, creating a force on the blade, forcing them to rotate. So the runner is spinning and the force acts through a distance. This way, energy is transferred from the water flow to the turbine. And the turbine turns a metal shaft in an electric generator, which produces electricity. So they are basically of two types. The first one is impulse, and the second one is reaction type. And impulse type are basically Pelton, turbo, cross flow, and reaction types are Francis and axial flow consist of the propeller, semi-kaplan, and kaplan. Coming on to the first type, which is the impulse turbine. An impulse turbine is driven by a high velocity jet of water. So as we can see, this is the penstock. So this is the water coming to the turbine, and here this is a here it is a nozzle is there to which, so when this water comes here, this governor, this is basically a support governor which can be moved forward or backward. So depending on the position of this governor, the nozzle opening differs, and due to which the amount of water and pressure of water also varies. So when this water comes here from the nozzle, high pressure water flows to the blades of these turbine in a tangential direction. As you can see, it is a tangential direction. So here this is high energy water, and after coming in contact with the blades, the direction changes of the water and it flows into a tail race, and here energy is reduced. So the jet pushes on the turbine's curved blades, which changes the direction of flow, hence causes the force to act on the turbine blades. The force acts through a distance, and the diverted water flow is left with diminishing energy. So this is the diverted water flow, which is left with the diminished energy. So if the load on the turbine decreases, If the governor pushes the needle, so this is the needle, this is the governor here, it pushes the needle into it and thereby reducing the quantity of water flowing to the turbine. Impulse turbines are often used in the very high head applications. So where there is very high head, there these kind of turbines are used. So this is the basically a type of impulse turbine, as I told you, impulse turbine, Pelton, turbo, and crossflow. So this is a Pelton turbine. You can see they have a kind of cups, double cups. One is this one and the other is this one. It consists of wheel with a series of split buckets. They are basically kind of split buckets around its rim, and a high velocity jet of water is directed tangentially. So water is directed tangentially. Suppose it is coming this way. At the wheel, the jet hits each bucket and is split into half. So when the jet hits, it's split into half. It splits this way. If it splits here, then this water, as you can see, the bucket, it is kind of this. This is the bucket. So if water hits here, it will be split back here. So it will be split into two, so that each half is turned back and reflected back almost through 180 degrees. So it is kind of almost 180, only a small angle is there. Nearby, all the energy of the water goes into the propelling the bucket and the deflected water falls into a discharge channel. So this is basically the Pelton turbine. Coming on to the next one, which is the turbo turbine. It is similar to the Pelton turbine, but the jet strikes the plane of the runner at an angle 20 to 25. So here there is some kind of angle made. So jet will be striking here at some angle, at a small angle. Basically, if suppose we take it is 20 to 25 degrees C. So the water enters the runner on one side and exits on the other side. A turbo turbine can have a smaller diameter runner, and so this runner is smaller in diameter. This diameter is smaller compared to this one and rotates faster than a Pelton for an equivalent flow rate. For the same amount of flow rate, this turbine runs faster than the Pelton turbine. Coming on to the cross flow turbine, it is a drum-like rotor with a solid disc at each end. So this is a drum-like rotor with a solid disc at each end. This is also, it is a solid disc and a gutter-shaped slats. These are the kind of gutter-shaped slats joining the two discs. So they are joining these two discs. A jet of water enters the top. As we can see, if it enters this top, it enters once into this blade, then comes out from here and then again enters to the in this plate in this blade. So basically, a single run of water is entering twice into this turbine. Water enters the top of the rotor through the curved blades, emerging on the far side of the rotor by passing through the blades a second time. The shape of the blade is such that on each passage through the periphery of the rotor, the water transfers some of its momentum before falling away the little residual energy. So here some energy is transferred, then some amount of energy is transferred here, and the water coming here is with the least energy. Now coming on to the other type, that is the reaction turbines. In reaction turbines, the water enters the runner partly with pressure energy and partly with velocity head. They must be encased to contain the water pressure or they must be fully submerged in the water flow. In this turbine, the runner blades rotate with respect to guide vanes opening. Here, some kind of guide vanes are provided to direct the flow of water in a particular direction. So, as the sudden decrease of load takes place, the guide vanes limit. So, these guide vanes are responsible for the direction of water, directing the water into the turbine. So, if there is decrease of load on the turbine, then these guide vanes may decrease the water flow. So most water turbines in use are reaction turbines and are used in low and medium head applications. The two types mentioned are the Kaplan turbine and the Francis turbine. Okay. So coming on to this uh, reaction turbines, type of these reaction turbines, the first one is the propeller type. So basically guide vanes, we are talking about these things. These are the guide vanes which basically limits the flow of water in a particular direction. It won't go in this direction. So if water comes from here, it will be coming in this direction only. So they are similar in principle to the propeller of a ship but operating in reverse mode. A set of inlet guide vanes admits the flow to the propeller. So due to these guide vanes, water is limited to this area only. And those are often adjustable so as to allow the flow passing through the machine to be varied. So they can be adjusted to mean to adjust the flow of water to the propeller. Now, Francis turbine, it is essentially a modified form of propeller turbine. So, in which water flows here, it flows radially. So, if it enters from here, it goes in here. So, it is basically entering the turbine in radial direction and is turned to emerge axially. For medium head schemes, the runner is most commonly mounted in a spiral casing with internal adjustable guide vanes. So here also some kind of internal adjustable guide vanes are provided. So these are the guide vanes. So due to these guide vanes, it can enter here only. Water can enter here only. Now coming on to this, one of the characteristics of hydro turbines, that is the specific speed. This is a characteristic which may give us some information about the turbine. So, the specific speed for various specific speed of a turbine is basically the speed of geometrically similar turbine in which would produce a unit power of 1 kilowatt and unit head of 1 meter. The specific speed of turbine is given by the manufacturer and refers to the point of maximum efficiency. So, the specific speed may tell us about the maximum efficiency. So it is dependent, as we can see, it is dependent on the turbine speed in RPM, then the rated power in kilowatt, and head in meters. So the formula is NS equals to, that is, specific speed is equal to turbine speed into under root of rated power upon H, that is head to the power 5 by 4. So this is the formula of specific speed. So different type of runners have different specific speed, and here we can see that the propeller and coupler type runners have the highest specific speed, that is 342,000 RPM. So selection of turbine type can be done by seeing this turbine application chart, which is a graph between which is a graph between flow versus head, and these black lines are basically the rated power, that is zero point 0.1 megawatt power, 1 megawatt power, 10 megawatt power, and 100 megawatt power, and 1000 megawatt power. So in different regions, different kind of turbines are applicable. So this yellow region we can see in this, if our characteristics, if our given specifications match, come under this area, this region, then Francis turbine will be used. And if it come under this green area, then it is the turbo turbine will be used. And in the red area, Pelton turbine will be used. And in the blue area, Kaplan turbine, and in pink, cross flow turbine will be used. So using this chart, we can determine, given based on our given specifications in the question or our application, we can easily determine that which kind of turbine will be the most suitable one for our application. Coming on to the power generation calculation. So standard equation for calculating energy power is, it is head into flow into efficiency upon 11.8. So this is basically a index, that is, this is basically a conversion index of feet and of conversion of that meter to feet or seconds to kilowatts. So this is simply conversion index. And this is the head, the electric power in kilowatt is taken head, the waterfalls in feet, and then the amount of water flowing in cubic feet per second, that is CFS. And another thing is the efficiency of a hydropower plant. As I told earlier also, efficiency depends on the efficiency of different working equipment, different working machines. So the efficiency of turbine into efficiency of generator into efficiency of gearbox. So if we multiply all these three, we will get a weighted average efficiency that is given here. So it is basically, if we take it, suppose we take 88, 96, and 98, so it will be 0.88 into 0.96 into 0.98. So that will be the weighted average efficiency. So let us come to the other kind of energy that we will be talking about, that is also a source of energy. Uh, that is also under development nowadays, which is the geothermal energy. It is also renewable energy source. So what is basically geothermal energy? So we can see from the word itself, geothermal. So basically it is the heat energy extracted from the earth. Geothermal energy is the thermal energy generated and stored in the earth. So as we can see that, suppose this is the center of earth. So in the center, the temperature, center of earth at the center, temperature is very high, that is about 500 degrees C, which starts to decrease as we move towards the surface. So it starts to decrease. So suppose this area, it is 4000 degrees C, and up to the, when we come on the surface, which is the green belt, here the temperature is ambient temperature, that is around 25 degrees C or 25 to 30 degrees C, basically ambient temperature as we come up to the earth surface. So this temperature, this high temperature starts to decrease as we move toward the Earth's surface. The geothermal energy of Earth crust originates from the original formation of planet. So this heat is generated here in the core of the Earth due to various kind of radioactive decay of material or various kind of reactions going inside the Earth's surface. So the geothermal gradient, which is the difference in temperature between the core of the planet and its surface, drives a continuous conduction of thermal energy in the form of heat from the core to the surface. So high energy and pressure in Earth's interior causes some. So here, this is almost a molten material, which is basically called the magma. And here some molten rocks are present, causes rocks to melt and solid metal to behave plastically, resulting portion of the metal convecting upwards since it is a lighter than the surrounding rock. So here some kind of molten rocks are there, then some kind of rocks here are there which are not molten but are very but are very hot due to the heat which is convected from this liquid material from below. So if rocks are present here, they are also at very high temperature. So rock and water is heated in the crust sometimes up to. So if there is some kind of water and rocks here present, so they may get heated up to 370 degrees C. And this water only, which is at high temperature here, we can use this water to extract energy from this water, to extract heat energy from this water. Coming on to the various applications of geothermal energy. So basically, it is used either in the direct way or in indirect way. Indirect way is basically conversion of this heat energy by heat recovery into electrical energy. And direct way is providing heat for buildings, hot springs used as spas, heating water at fish farms, provides heat to industrial processes, raising plants in greenhouses, and drying crops. Now let us come on to different usage of how to use coming on to direct use of geothermal energy. So basically, it can be used in two types, either in the closed loop or in the open loop. So let us talk about closed loop. Suppose this is the closed loop. Suppose this is our house. So a pipe will be taken from our house and it will go deep into the earth surface. Coiling will be done. Suppose this pipe is taken into the deep into the earth surface. If suppose here we have our geothermal energies. Mean we can extract geothermal energy from this area. So this goes deep into the earth surface, extracts the energy, thermal energy from deep below. If suppose water goes in this pipe, it goes deep below. gets heated up, and then hot water comes up from this pipe and it goes into our houses. So this is basically the closed loop. Coming on to the open loop, here we can see if we have, suppose this is a water chamber we have made, suppose. We take hot water from this pipeline, suppose it goes, we take hot water from here, and suppose there is some area, from here we can take geothermal energy. So this tank will be taking a pipeline to below the earth, and it will be coming back here. So this tank will be getting its hot water from this geothermal energy, and this storage tank, this hot water in this storage tank will be taken in our houses. So basically it is not closed loop. So we are taking energy from this hot water, or either we are using hot water directly from here, and this hot water we are getting by extracting energy from down the earth. Now coming into the mechanism for electrical energy production. So the basic mechanism is, if suppose these are the molten, this is the magma, these are the molten rocks here, and these are the hot rocks. These are not in the molten state, but are in hot, but are hot state due to the by taking heat from this molten rocks. So these are rocks and water is present here. So if suppose we water is there, then at high temperature, if there is very high temperature, then water may form, will may heat up to very high temperature and may form steam and can go up here. And here, after this steam comes in contact with this turbine, uh, where uh, where its energy will be, where this steam rotates the blades of the turbine, and this mechanical energy from generator is converted to electricity. So sometimes it is possible that steam is not present. Sometimes it is possible that high temperature, high pressure water is there. If suppose temperature is high, but not that high to form the steam, so only water will be present. So high temperature, high pressure water will be present. Then here some kind of flash drum we can install some kind of flash drum in the this system. So here pressure will be released, converting this water into steam, which in turn will be taken to the turbine for the electricity generation by the generator. So basic steps involve the injection of water. So firstly, we will and after the extraction of the heat energy, the residual water will be given back, which is mean not very hot water. After recovering all the heat and steam power here, the water will be given back down to the earth for further heating and continuation of this cycle. So this cycle will be continuing likewise. So the steps involved are the injection of water. So firstly, we will be injecting water from here, then it will be getting heated up into steam or water, then it will be going above, then to the turbine, electricity will be generated, residual water will be given. So this will be complete cycle. Then production of heat, then use of the steam for heat application or electricity production. So now this one, as I told that if we don't get steam, then what will happen? So suppose in this case, suppose we get high temperature, high pressure steam we are getting here. So sorry, high temperature, high pressure water. Then this water will go up here to the heat exchanger after the heat recovery. It will be giving back the cold water, and after heat recovery, it will go to the turbine and then generator and and heat sorry, electricity production will take place. And if sometimes some amount of water is also given to the condenser, this is also mean less cold water, less hot water than this. is, but it is also hot water. So some condensation will take place, and then heat recovery in the cooling tower can take place. So likewise, we can completely recover the heat that will be taken up by the water from below the earth. And if we can also some kind of flash drum can also be installed in between for the conversion of this high temperature, high pressure steam to high temperature, high pressure water to steam. Coming on to some different options for electricity generation by the geothermal energy. So there are three types of power plant. The first one is dry steam power plant, then the flash steam power plant, and the binary cycle power plant. So dry steam is basically when the temperature is very high, suppose 350 to 370 degrees C temperature is there below the earth, then the water which will be injected here, it will convert directly to the steam. So steam will be given out. So this steam will go to the turbine, and the turbine will rotate, and then in turn the shaft of the generator will rotate, producing the electricity. And then the residual water, or the after the recovery of all the heat from the steam, residual water will be given back into the injection well again. Then the other one is the flash steam type. So if the temperature is a bit lower than this one, if suppose the temperature is up to 180 to 185 degrees C, then high temperature, high pressure steam will not be generated, but a high temperature, high pressure water will be given up. So when this water will be given up, it will come in contact with the flash tank, where its pressure will be reduced, giving up the steam here to the turbine, and then again in turn it will be used for the generation of electricity by generator, and the residual water will be given back again to the injection well. Then coming on to the binary cycle power plant. So basically, if the temperature is more lower, that is about 1072, 182 degrees C, the water is very low, then temperature is very low, then we will be getting hot water, which will here we have hot water. Then here we will be having some kind of solvent, some low boiling solvent, which is basically called the working fluid. So this hot solvent, no, sorry, hot solvent, no. So this working fluid, that is the solvent, will it is kind of a heat exchanger arrangement. So this solvent will extract the thermal energy present in this water, will get heated up, will form solvent vapors, and this vapors will go to the turbine. Turbine blades will rotate, and the shaft will rotate, and generator will produce the energy, will the electrical energy. And this hot water will be then cold water, will residual water will be taken back to the injection. So this is basically binary cycle. This one cycle is the water cycle, and the other cycle is the solvent cycle. Coming on to some of the advantages and disadvantages involved with the geothermal energy. So basically the first advantage is it is renewable and sustainable, it is cost effective, constant supply is available, because obviously the temperature of earth is not going anywhere. It will be very high for the upcoming years also. So then it is environment friendly, small footprint, low noise. There is no problem related to noise because all the arrangements are below the earth. And low maintenance, huge potential, job creation is there, reduces fossil fuel dependency, and increases energy security. Although the advantages are there, some of the disadvantages are also there, which are basically the geographical limitations. It is not available at all places. This geothermal energy cannot be extracted. Suppose if we want to extract geothermal energy, it is not like that. I will dig a hole into into my garden, and I can extract geothermal energy. So there are some of the significant locations. So geographical location is also a factor. So for that, we need to some geographical considerations are also need to be taken. Large investment, initial investment is the large investment is required. Then environmental impacts mean uh, environmental impacts are like related to if we dig the hole, there may be collapsing of the land area, etc. Then sustainability concerns. And then seismic instability also is a concern that if suppose a large exploitation of the geothermal energy is taking place, it may cause instability in the various tectonic plates of the earth, causing different kind of natural hazards like tsunamis and earthquakes. Coming on to the global geothermal status, so we can see here these are the orange one is the direct use and power generation is the red one. So we can see that mostly in India direct use method is there. So basically we extract the thermal energy and use it in basically suppose water heating and I mean as I have told you there as hot spring or heating water for fish farms or providing heat for buildings, etc. So direct use is done in India mostly. And for power generation, very less countries such as Australia here and these areas in Russia and these areas here use this geothermal energy for electricity production. According to a recent study, there are 806 geothermal power projects in development globally with a combined capacity of 23,313 megawatts with the majority located in Asia, North America and Africa. However, the industry faces strong challenges everywhere. Projects need to secure government not only government approval but also public consent is also required. Sometimes local people cause opposition due to different factors. And financing is also a problem because it requires a high initial capital investment. Current global current geothermal power production involves in terms of upcoming projects. Individual countries such as Indonesia and USA are the leading countries in geothermal power production. It has more than 8,000 megawatt of projects in development. It is followed by US with around 61,000 megawatt in development. So these are the different countries in which we can see that US and Philippines produce the largest power, give the large, has more than 2,800, US has 2,850 megawatt generation of geothermal power and Italy. And after that, Philippines, Italy, Mexico, and all those later. And Indian geothermal energy potential, India also has estimates show that geological and geochemical, shallow geophysical, and shallow drilling data that India has about 11,000 megawatts of geothermal power potential that can be harnessed for various purposes. More than 200 hot springs locations are available in India, and the surface temperature it varies from 40 degree to 100 degrees C. Temperature is not very high, so, but it is in the range of 40 to 100 degrees C. So, main areas are Tatapani in Chhattisgarh, Unai in Maharashtra, Godavari Basin Manikaran in Himachal Pradesh, Kuga Valley in Jammu and Kashmir, Tuwa in Gujarat, and Jalgaon, Maharashtra, Bakreshwar in West Bengal. So, in spite of this, the utility of geothermal power projects do not have not been exploited at all due to a variety of reasons. The power primary reason is the availability of plentiful because in India we have plentiful coal which is available at very cheap rates. So, why to shift to some other kind of energy in which initial investment cost is very high and so with increasing environmental problems but with increasing in environmental problems related to coal based projects, India is now focusing on more eco-friendly energy sources. So maybe in the future, this geothermal energy potential will be highlighted by the Indian government. Coming on to the fourth kind of energy, which is the waves and tides as a source of renewable energy. Just a second. Coming on to the waves and tides as a source of renewable energy. So as we know, waves are basically created by energy passing through the water. So waves are basically present in the oceans. We can see the coming of water to the shore and going back. That are sorry, they are basically tides, and waves are present are available in the sea, in the oceans and sea. So waves are created by energy passing through water, causing it to move in a circular motion. Waves transmit energy. So the energy is present in waves, not in water of the ocean, across the ocean. And if not obstructed by anything, they have the potential to travel across an entire ocean basin. So waves are basically of two types. Waves are basically caused by wind. So wind-driven waves or surface waves are basically caused by the friction that is taking place between the flow of wind and the ocean surface water. So it is basically created by the friction between the wind and surface water. So as wind blows across the surface of the ocean or lake, the continual disturbance creates a wave crest. These types of waves are found globally in the open sea. So basically, this is the diagram. We can see this is the ocean floor and this is the calm sea level. So due to the flow of the wind, there is the formation of waves. So these are basically the motion, this up and down motion of water are called waves. This is the amplitude, this is the wave height, and these are the wavelength, and this is the crest, and this is the water depth. So wave Another more another kind of more hazardous waves are can be caused by severe weather, which are hurricanes. Other hazardous waves are tsunamis, which can be caused by underwater disturbances that displace large amount of water quickly, such as if there is some kind of earthquakes or landslides or volcanic eruption going on the sea level, then these are the most hazardous kind of waves, which are the tsunamis. And the gravitational and another kind of thing that is another kind of term which is the tidal waves. So these are basically due to the gravitational pull of the sun and moon on the earth. So the gravitational pull of sun and moon on earth causes these waves, and so these waves are basically called tides. So they are called the tidal waves. Kinetic energy of waves and tides can be converted to usable forms called such as electricity. So wave power converts the periodic up and down movement of the ocean waves into electricity by placing equipment on the surface of the ocean that captures the energy produced by the wave movement and converts this mechanical energy into electrical energy. So we will be talking further what kind of equipments are installed for the conversion of this wave energy into electrical energy. Coming on to wave energy production, it is basically three kind of devices are present. The first one is shoreline devices, which are fixed or embedded in the shoreline. That is why they are both in and out. So it is some amount is below the sea and some amount is above the sea. Near shore are at 20-meter water depth. So this water depth when it is 20 meter. So here these are the near shore devices. Offshore devices are situated at more than 30 meter. So more than 30-meter diameter. So more than 30-meter depth of water where sea depth is more than 30 meter, their offshore devices are installed. So no need of significant coastal earthworks. So these are small vertical devices either fixed or directly to the ocean floor or tethered by a chain that absorbs the wave energy from all directions. Either they are fixed on the sea floor or either they may be floating or I mean uh, as this is floating and this one is deep down below it is floating. So uh, two types are there, either fixed or either floating. So these devices generate energy from bobbing or pitching action by up and down motion of these floating devices. Uh, these floating devices generate electricity as they cause this up and down motion. Typical wave energy include floating buoys, floating. So these devices, some typical devices are floating buoys, floating bags, ducks, and articulated rafts. So these devices converted the up and down pitching motion of the waves into rotary movements or oscillatory movements in a variety of devices to generate electricity. Different kind of devices are attached. If suppose there is some kind of chain attached to it from here, so it will be causing some up and down motion, and this up and down motion in this chain will be harnessed to this energy generated in this energy absorbed by this chain will be will be converted to generate electricity. So one of the advantage of floating devices over fixed devices that is that they can be deployed in deeper water where it can be installed anywhere in the Earth's surface. Sorry, anywhere in the ocean uh, without concerning about the depth of the sea floor. So at very deeper ocean areas also it can be installed. So at very areas, we can say that the wave energy is much greater compared to the deeper areas. So these floating devices have this advantage that they can harness more energy. Coming on to the tides. So what are tides? They are basically the periodic rise and fall of seawater occurring once or twice in a day, driven by the gravitational attraction of sun and moon on Earth. So when a landmass lines with the Earth-Moon system, the water around it is at high tide. So suppose this is in line, Earth and Moon are in line. So this land area is in line with the Earth and Moon. So here it is the high tide. And when this area is at the 90 degree of the Earth and Moon system. So it is at 90 degrees. So here and here, low tides are present. High spring tides occur when the sun and moon lines up with the earth, and this occurs whether they are either on the same or opposite side, either here or on the opposite side. Both areas, high tides will be there. Low neap tides occur when the sun and moon line up at 90 degrees. So these are at 90 degrees. So here low tides will be there. So flood currents, there are two kinds of current. Flood current is when the water comes to the shore. If suppose this is ocean and this is beach, this water comes to the beach area. This when it comes this side on the beach, it is the flood current. And when it goes back, when this water from the beach goes back, it is the ebb current. This is the flood current. Tidal energy, it is a form of hydropower that transforms the energy obtained from the tide into useful forms of energy, mainly electricity. The tidal generator converts the energy of tidal flow into electricity. Greater tidal variations and higher tidal current velocity can dramatically increase the potential of a site for tidal electricity generation. So, as if the height of the tides is more and high tidal current is there, so that also decides the potential of a site for tidal electricity generation. During high tide, the water flows into the dam, and during low tide, flows out, resulting in turning of turbine. Therefore, the tidal generators are designed to produce power when the rotor blades are turning in either direction. So these turbines used in these tidal power plants, it is generated, it is manufactured in a way that it can rotate in both directions. So, because once the water tides will go towards the sea, so it will rotate in one direction, and then during the ebb current, when it will be going back into the sea, this waves will be going back to the sea, then it should rotate in the other direction. So, during the both the directions, uh, you can generate electricity. Because the Earth's tides are ultimately due to gravitational interaction with the Sun and the Moon, the Earth rotation tidal power is practically inexhaustible and classified as renewable energy source. So, because it is due to the gravitational pull of Moon and Sun on Earth, this energy is practically inexhaustible because this cycle will not be ending anytime. So basically, this is if suppose the tide is coming, so here water height is very much and here water height is low. This is the tidal basin. When the tide comes during the uh, flood current, water moves goes through this turbine and it rotates, thus rotates and in turn rotates the shaft of the generator producing the electricity. And likewise in the ebb current, when this this water goes back from the beach to the ocean, then also again this turbine will rotate in the other direction. If suppose here it will rotate in this direction, then in ebb current it will rotate in this direction and in the second cycle also producing the uh, electricity. So there are three main ways or three main parts to harness tidal energy. These are tidal turbines, tidal barrages, and tidal lagoons. So tidal turbines are basically similar to uh, wind turbines, but they, as we know that the density of water is more than air, so the blades of these tidal turbines are basically shorter and stronger compared to the wind turbines. So tidal turbines usually use similar energy to similar technology to wind turbine, although their blades are much shorter and stronger. The water current turns the turbine, which in turn activates the generator and produces electricity. System work best when there are very strong tidal zones. Upfront cost of these tidal streams system is very high, and also installation and maintenance cost is difficult. So there is this problem of maintenance and installation is a problem. Obviously, deep down the ocean, it is a problem. Cheaper and has less environmental impact than other tidal systems, which uses barrage. Here also two types of turbines are there, horizontal axis turbine and vertical axis turbine. As we can see, this is the horizontal axis turbine and this is the vertical axis turbine. So we have discussed in detail about these turbines in during wind energy. So we will not be discussing here in much detail. Coming on to the tidal fences, this is a kind of civil structure. It is made. A kind of fencing is made with some gates. Other form of tidal energy include tidal fences, which uses individual vertical axis turbines that are mounted with a fence structure. So these gates are there, in which individual turbines are uh, installed. Here individual turbines are installed, so during the flow of the uh, water, these individual turbines rotates, in turn generating the electricity. Another thing is tidal barrages. They are basically dam like structure, as we can see, used to capture the energy from masses of water moving in and out of the bay or river due to tidal forces. So tidal barrage first allows water to flow into the bay or river during high tides and releases the water back during low tides. So firstly, the water will flow into the bay A during high tides, and then it will flow back during the low tides. So done by measuring the tidal flow and controlling the flow floodgates at key times of the tidal cycle. Turbines are placed at the sluices to capture the energy as the water flows in and flows out. Basically, this is the sea and this is the basin, or as we can see in this diagram. If we make suppose this is suppose it is a barrage. So when high tide will be there, water will flow to the basin from these from this barrage, and here in the sluices, turbines are installed. So during the flow of the water, turbines blade of the turbines will move, producing the electrical energy. Coming on to the tidal lagoons, as we can see here, it is the sea, and this is the land and shore, and this is a enclosed area. In the barrage, it is a mean very open area is enclosed with this barrage, but in the lagoons, an enclosed area is taken. From here, sea gates are there and water comes in from here. And when during the tides, water flows through this turbine house, blades of these turbines rotate and generate electricity. Coming on to the global tidal energy scenario, so we can see here US has very high wave energy potential and some tidal energy potential as well. Whereas here Norway, we can see it has a good tidal energy potential. But India, we only have wave energy potential, no tidal energy potential is there in India. Indian tidal energy scenario, we can see there are three key areas. That is the Gulf of Cambay with a maximum tidal head of 11 meters, then Gulf of Kutch 8 meters, and Sundarban West Bengal 5 meter. Average of Gulf of Cambay is 6.77, and the Gulf of Kutch is 5.23, and Sundarbans is 2.97. And the potential energy potential is highest in Gulf of Cambay, that is 7,000 megawatt, whereas less than 100 megawatt in Sundarbans. As we can see, that head is also very low here. So the projects which were planned earlier were abandoned due to high capital cost, and India needs to consider factors like industry. And because in India, as we know, that we still focus more on the capital cost, etc. Still, there is this notion that uh, sorry, uh, still focusing more on the environmental impacts, we still focus more on the capital cost, etc. Therefore, these renewable energy sources, I believe, are not that flourishing in India compared to other nations. So in India, I guess people need to consider factors like environmental impacts of of these projects in the long run and the strong tidal energy policy to attract investors to projects. India, as we know, it has a long coastline. So it is believed that India has a higher wave energy potential. So if we consider all these factors, uh, wave energy production is a very good alternative to different non-renewable energy sources. Now coming on to some of the assignment questions. Am I audible?
Yes,
Hello.
ma'am.
Okay. Should I start with the questions? Should I start?
Yes, ma'am.
Okay. So coming on to the assignment questions. The first question is, which of the following is not a type of impulse hydro turbine? Would you like to answer? Hello.
Francis.
Okay. So this is the correct answer. So basically, Pelton, Turbo, and Crossflow are impulse hydro turbines. This one is Francis, and one more was there Kaplan, which are the basically it is reaction type hydro turbine. So which of the following is not a type of axial flow reaction hydro turbine? Do you know the answer? Okay, let me tell. So as we have studied axial flow reaction type, it is basically of three types: propeller type, semi-Kaplan, and Kaplan. So this Cross flow type is not a type of axial flow reaction hydroturbine. It is basically, as we see in this question, it is impulse hydroturbine type of turbine. Wave caused, third question, wave caused by the gravitational pull of sun and moon on the earth are called. Just now we studied. So they are the tidal
tidal
waves.
waves.
Okay. Oops. Which of the following is not a type of axial flow reaction hydroturbine? Sorry. I guess there is some problem with the question. Just a second. Give me a minute. Um, Okay. Specific field. Okay. So in this question, sorry for this inconvenience. So in this question, what we have to do, we have to match these turbine types with their specific speeds. So let me show you. Basically, here we can see, as I've told, different type of runners have different specific speed. So here we can see propeller and Kaplan has highest specific speed of 342,000. Then Pelton has the lowest of 12 to 30. And after that, Turbo, Crossflow, and Francis. So we come to the question. So here, as I've told, Pelton has the smallest. Okay. So the smallest here is 12 to 30. So R will be 2. Then after that, after Pelton, it was Turbo, then Crossflow. So Crossflow after that, it is 2280. And then comes the Francis, which is the highest among all these three. So it is basically P3, Q1, and R2. P3, Q1, R2. Is it clear?
Yes, ma'am.
Okay then. Question number 5. Which of the following is the indirect exploitation of geothermal energy? As we have seen, the direct exploitation is basically the direct usage, which is done basically providing heat to buildings, hot springs, then heating water at fish farms, etc. But in electricity generation and heat recovery, there is some, requirement of some amount, some kind of conversion, etc. Some kind of machinery is required for the conversion of one form of energy to another. So it is not the direct exploitation. So basically, the answer is electric generation and heat recovery. Now coming on to one of the numerical questions, you also try. Let me read out the question. Let me tell you what is given in the question. So a dam is 357 feet high, and the head, the distance from the waterfall is 250 feet. So basically, as we have studied, that mostly the power generation. Sorry, let me study first. Let me read it first. The typical flow rate is 2000 cubic feet per second. Calculate the power generated by the power plant. Assume the turbine and generators are 85% efficient. So this is basically kind of average efficiency given. So dam height is given and head is given. But we have seen that our power generated by the power plant is mostly dependent. In all of the cases, it is dependent on the head. So this is not required. This head is required, which is 250 feet. And the typical flow rate, which is Q, is given 2000 cubic feet per second. So what we have to find out, we have to find out the power. Basically, as we have studied, power of the turbine here. So the standard equation is power equals to head into flow into efficiency upon 11.8. So basically, we will be using this formula, and flow we have been given in cubic feet per second, height is given in head is given in feet, and we will be calculating our power in kilowatt, and efficiency is also given. So the formula is power equal to head into flow into efficiency upon 11.8. It is basically conversion index. So head is given 250 feet into flow is given 2000. We don't have to convert anything because it is asked in CFS only, it is asked in feet only. And efficiency is given 0.85. Calculate and tell me what is the answer. Hello.
36017.
Okay, it is 36,017 kilowatt is the power generated by the this is our answer. Okay. Coming on to the next question. A mountain stream flows over a terrain where a micro hydropower plant is possible, where a effective head is 40 meter is built and a flow rate of 0.5 meter cube per second can be maintained. How much power can the head? Just a second. A mountain stream flows over a terrain where a micro hydropower plant is possible, where an effective head of 40 meter is built and a flow rate of 0.5 meter cube per second can be maintained. How much power can the power hydropower plant generate per year? Assume plant efficiency of 80%. So let me tell you what is given first. We are given the flow rate, which is 0.5 meter cube per second. Then head is given 40 meter and efficiency is 0.8. So as we studied power generated in the hydropower plant, it is given by 9.81 eta QH. So it will be 9.81 into zero point 0.8 into zero point 0.5 into Tell me what is the oh calculate and tell me. Oh,
Oh, yes, ma'am. Just a second.
okay, okay. Take your time. Okay, just let me calculate. So it is 156.96 kilowatt. Did you get the same?
Yes, ma'am.
So if we write, let us convert it in megawatt for our convenience. So we saw that energy required per year, it will be power into, sorry, energy generated per year, power generated per year, it will be power into time. So it will be 15696 and time taken is in hours. So in a year, how many hours? 365 into 24 hours. So it will be 1374.96 megawatt, approximately 1375 megawatt energy. Okay,
Yes, ma'am.
coming on to the next question, which is also numerical. Okay, then. A geothermal aquifer supplies hot water with a wellhead temperature of 80 degrees C at the flow rate of 15 liters per second. So the temperature of the geothermal aquifer, so the temperature below the earth, it is 80 degrees C. Sorry, temperature below is not 80 degrees C. The uh, the temperature of water which is produced after heating with the geothermal energy, it is 80 degrees C. And the flow rate is 15 liter per second. The heat energy is used to supplement a direct heating unit above a datum temperature of 45 degrees C. So we are producing this heat using this water to a heating unit which is at a temperature of 45 degrees C. So obviously we need to increase this temperature from 45 to 80 degrees C. If the geothermal heat is used for 150 days each year, this is the working days, how much oil is saved annually if the overall combustion efficiency of the oil burner is 75? So if this amount of heat is used for 150 days per year, so if we are not using geothermal energy, then if suppose we are using oil instead of that, so how much energy that oil will be producing? We have to calculate that. We have to calculate that how much energy if we use the oil, how much energy would be used. So that is obviously saved when we are using geothermal energy. Assume the heat of combustion of oil is given and the specific heat of water is given. So let us first calculate flow rate, which is given in 15 liters per second. So let us first convert this. It is given in per second, so we have to convert it the amount of flow rate for 150 working days. Okay, converting it to day. So seconds present in a day is 3600 into 24. It will give us liter per day. As we had liter per second, it will be giving us liter per day. Then it is 5600 into 3600 into 24. So how many days? 150 days. So it will be 194.4 into 10 to the power 6 liter per working year. Basically, a working year in this question consists of 150 days. So we can say that it is this many liters per working year. Is it clear?
Yes, ma'am.
Now calculate the volume of water transferred per working year. Is 194.4 into 10 to the power 6. It is in liter. We want it in ml. If we take it in ml, suppose it will be this. Okay. Now, mass of water transferred per working year. So if we say that 1 ml, we know that 1 ml equals to 1 gram. So we can say this is the mass of water taken transferred per working year, or we can say it is okay. Should I change the page?
Yes, ma'am.
Okay. Then temperature difference is given 80 minus 45, which is 35 degrees C. Then heat transferred per working year will be MCP delta T or MS delta T. So M is mass, we calculated it as 194 into 10 to the power. This is in kg, converting it in grams. Then specific heat of water is given 1 calorie per gram degree C. Okay? Then S is 1, then delta T is 35. So it will be 6.804 into 10 to the power 12 calories. Okay. So now oil saved per working year, if we take that 100% efficiency is there in the combustion of oil, 100% oil gets converted into heat. If we take that, then if 100% efficiency is there, then as heat of combustion of oil is 10 to the power 10 calories per ton. So this amount of heat is generated per ton if 100% efficiency is there. Then it will be giving us, so this much oil, this amount of oil, this amount of oil will be used if there is 100% of efficiency. This amount of oil will be used for the uh, generation of heat to heat in sorry, to heat this heating system from 45 to 80 degrees C for 150 days. We will have to use this 680.4 tons of oil if we are not using geothermal energy. So this amount of oil is saved if 100% efficiency. But the question gives that it has oil burner as 75% efficiency. So for the uh, For the so the amount saved with 75 ml oil saved with 75% efficiency, it will be oil in 100% efficiency upon efficiency, it will be giving us 907.2 tons of oil. So we saved 907.2 tons of oil. So the answer is this. Is this clear?
Yes, ma'am.
Okay, then let's move forward. Coming on to the ninth question, which is hazardous waves called tsunamis can be caused by natural activities such as. So as I told, the tsunamis are caused by some kind of earthquakes or landslides or volcanic eruptions which are taking at the ocean surface. So the answer is all of the above. Question number 10. Which of the following is the example of reaction turbine? Okay, these questions. So reaction turbine, basically we can see here that both of them are reaction turbines, Kaplan turbine and Francis turbine. They both are reaction turbines. So answer is both A and B. Tidal turbines use similar technology to wind energy, although their blades are much dash and dash. As I have told, due to the higher density of water, their blades are designed in a way that they are shorter than the wind turbines and but more stronger than them. So the answer is shorter and stronger than the wind turbine. Coming on to one of the numerical questions again. So the question is a goods train consisting 55 wagons and traveling at a speed of 40 km per hour. The average weight of each wagon is 20 ton force. Calculate the time required to produce the equivalent amount of electrical energy by a small tidal power plant of 20 kilowatt capacity. Consider 1 kilowatt hour equals to 367098 kg force per meter. Kg force meter. So let us solve this. A goods train is there which consists of 55 wagons, and the average weight of each of the wagon is this. It is traveling at a speed of 40 kilometers per hour. So we have to calculate the time required by a small tidal power plant whose capacity is 20 kilowatt, whose capacity is 20 kilowatt to produce equivalent amount of electrical energy as by the this goods train. So the weight of goods train, it is 55 wagons. So we will calculate the total weight. As we know, it is given 55 wagons and weight of each is given 20 tons. So 20 ton, that is 20,000 kg force. Mass of goods train by 9.81 will be 112130.479 kgf second square meter. Speed of train is given 40 kilometer hour, which on conversion gives 11.11 meter second. So now the kinetic energy stored in train. As train is also moving, so the kinetic energy stored in train is half mv square, which will be half into mass we have calculated here 112130.479 into 11.11 square, which will give 6920250.248. Something is wrong with the pen. Just a second. Which on dividing, as we can see, the conversion is given 1 kilowatt hour. On dividing it with this, is it okay? Should I turn the page?
Yes, ma'am.
It gives us 18.85 kilowatt hour. This is the amount of kinetic energy stored in the train. We have been given capacity of our tidal power plant in the question as 20 kilowatt. So the time required to produce similar amount of energy as by the train, it will be, this is by the train and this is our capacity. So it will be 0.9425 hour, which in minutes will be 56 point, around 56.4 minutes. Okay.
Yes, ma'am.
Now coming on to the next question. The world's largest tidal power plant installation is. The answer to this is Shiva Lake Tidal Power Plant, South Korea. Sorry, this was not included in the slide, so I am telling you the answer is Shiva Lake Tidal Power Plant in South Korea. In hydropower plant, energy is produced by using the kinetic energy of water to turn the turbines is the and potential energy stored in water at heights. So both potential energy which is stored in water at heights and kinetic energy of water which is used to turn the turbines, both A and B are used for the production of energy in hydropower plants. 15th question. What causes some rocks to melt and solid matter to behave plastically in Earth's interior? The answer is high temperature and high pressure below the Earth's crust. It causes the rocks and salts under the Earth's crust to melt. 16th question. Which of the following properties corresponds to short line devices? The first one is shoreline devices, near shore devices, and offshore devices. I guess that is shoreline devices. So it is basically both fixed or embedded. That is, they are both in and out of the water. They are fixed to or embedded in the shoreline. I guess this is shore. Which of the statement is false for tidal energy? The answer is kinetic energy of waves and tidal tides cannot be converted to usable form of energy. Because as we told that the as I told in during the tidal energy part also, the energy stored in the water is not used in the tidal power plant, but the energy stored in the waves is used. So this is the answer. Sorry. There's a sorry for I mean it is asked which of the statement is false. So obviously this is false because all the time, I mean all along in the tides also we are converting this tide kinetic energy of waves and tides only to convert it into different forms of energy. Coming on to another numerical question, which is a turbine develops 8,000 kilowatt when running at a speed of 165 rpm and a head of 45 under a head of just a second. Determine the specific speed. So as during the theory part, we have seen the specific speed formula. So putting all the things are already given in the question. N is 165 rpm, P is 8,000, and head is 45 to the power 5 by 4. After calculating, we will get 126.62 rpm. Is it clear?
Yes, ma'am.
Now coming on to the 19th question. The tidal range of a bay could approach 15 meter in approximity. About 100 billion tons of water flows into and out of the bay. If suppose this is the sea, this is the bay. It is flowing into the bay, and if suppose here 100 billion ton of water is flowing into this bay and coming back. So bidirectional turbine is required. And if suppose this is the height difference, it is given 15 meters in one side. Flows in and out of the bay in one side. We'll calculate the potential tidal energy of the bay in this extreme case in 1 year by using bidirectional turbines. Gravitational acceleration is given 9.8 meter per second. So these are, sorry, I forgot to give all this in the question. These is given in the question. Number of tidal cycles per year, and PYC is given by 24 hours, that is in a day, and per year is 365 days upon 12.4 hours. This is basically the time taken by one tide to occur in a day. So it comes to be 706.5 cycles per year. This is uh, all the time it is constant because this time doesn't change. So number of times for tides to drive turbine. So in a single cycle, turbine is driven twice, one in and out. So it will be two times of NCYC. And so this N comes to be 1413. 2 into 706.5. It comes to be 1413. The total tidal energy we will be calculating. It is number of times turbine is rotated into potential energy by 2. So by 2, why this by 2 is there? Because this head, it is not constant all the time. This head at the high tide, it becomes maximum 15 meter. Then after that high tide, it starts to decrease, then comes to 0. So it is constantly changing. Therefore, we are taking the average. So height is taken h by 2. 100 billion, that is 10 to the power 100 into 10 to the power 12, which is 10 to the power 14. It is in kgs, 10 to the power 14 kgs. Mean 100 billion ton, that is 100 into 10 to the power 12 kg. So it is 10 to the power 14 kgs. 9.8 into 15 upon 2. It will be coming as 1.0396 into 10 to the power 19 joule. So 1 joule is equal to 2.77 into 10 to the power minus 6 kilowatt hour. So by this conversion, we will get it here as 2.87 into 10 to the power 12 kilowatt hour. Is this clear? Am I clear?
Yes, ma'am.
Okay. Let us move to the next and the last question for the day. The question is if the tidal range of tide at a particular place is 10 meter. So it is basically the height is given 10 meter. Calculate the potential energy content of the water in the basin at a high tide if the tidal power plant has a surface area of 10 kilometer square. Assume the surface density of seawater to be 1025.18 kg per meter cube. If suppose this is the sea and this is our basin, and the surface area of this basin is suppose 10 kilometer square. So we have to calculate the potential energy content in. So potential energy will be mgh. So let us calculate firstly the mass density of seawater is given. So here we will be mass is volume into density, volume is area into height is given, volume of this basin, and here rho. So mass is area into height into rho into g into h by 2. Here h by 2 I have told earlier why, because we have to take the average. So it will be, so the converting it into meter square area, then height is 10, density is 1025.18, G is 9.81 into height is 10 by, the answer will be 5.028 into 10 to the power 12 joule. Is this clear?
Yes, ma'am.
So this is the last question for today's class. Is it clear? If you have any other question or any other question you want to see,
Can you please show the first slide of the PPT?
this one or the next?
The next one.
Do you have the link for, I mean, the Google Drive link for all these PPTs?
Yes, ma'am.
Okay, you can easily access from there and you can even watch the videos again if you want on the YouTube. Okay,
Yes, ma'am.
so everything clear for today?
Yes, ma'am.
So should we end the class?
Okay, ma'am.
Okay, thank you.